Good day. Today we'll be discussing about the governing equations that are used in computational fluid dynamics. Okay, so there are three equations that are used in CFD. First is the continuity equation. Second is the conservation of momentum, and the third one is conservation of energy. Okay, so for today's lecture, we'll only derive the continuity equation or the conservation of mass. So the conservation of mass, so these four equations are the different forms of the continuity equation. Okay, so they differ on how they are derived. Okay, so there are four models that are used. First is you assume that the fluid is a finite control volume that is fixed in space. Okay, so the second one is you assume that the fluid is an infinitely small element fixed in space. So kaning mga fixed in space, this is what you call the Eulerian model, okay, of the fluid mechanics, no? So this is the Eulerian model, and kaning sa right side, wherein it is assumed that the fluid is moving with the flow. Okay? So kung moving with the flow and ang imong fluid is assumed as a control volume na same ang iyang amount of mass, no? Wala na change sa iyang mass. And then you evaluate the control volume as it moves with the flow. So kanang model is what you call the Lagrangian description of fluid motion, or the Lagrangian model. Okay, so although kani silang upat, different ila ang the way it is written, but this is just the same. Okay, so pwede naman siya ma-convert from one form to another. Okay, so before we proceed in deriving, we will derive that for model, no? Before we do that, let's discuss first what about a topic nga magamit nato later on, which is the substantial derivative and local derivative. Okay, so imagine that you have a fluid element. So kani siya nga model, Lagrangian ni siya nga model, because it is assumed that a fluid element, no, travel ni siya from point 1 to point 2. Okay, so ang iyang density is defined by this vector. Rho is equal to rho as function of x, y, z, and t. No, ang iyang velocity, nasa velocity along x. Ang along x is u, ang along y is v, and along z is w. Wherein kaning u is also this is a vector field, no? Function is of x, y, z, and time. Okay, so sa pag-travel aning fluid element, mo-change na niya ang density. For example, kung density atong pangitaon, no? As it follows the kaninga path niya, mag-change na niya ang density. Nang change sa iyang density, you can get that by this one, no? You apply the Taylor series. So you apply a Taylor series. Say for example, you have the density at point 1. So kung given ka sa density at point 1, say for example, ang density niya diri is rho sub 1. And then gusto naman pangitawon ang density sa pag-abot niya sa point 2. No? So, unsay buhaton ni mana? You use the Taylor series approximation, no? Pwede ni approximate ang density at point 2 given ang value sa point 1. So, unsa na yung pagbuhat? Kani siya. You apply this one. Pero i-cut ni mo siya. Oh, never mind the higher order terms. I-cut ni mo sa diri, sa first derivative, no? So, saan sa metabuha na? Therefore, ang imo ang rho sub 2 is just equal to kaning f of a, which is unsay value niyo sa density at point 1 plus partial of rho with respect to x, x2 minus x1. x2 minus x1 is kani x2 minus x1. So, ang distance nilang duha. Okay? Plus delta rho over delta y, partial of rho with respect to y times y2 minus y1 plus partial of rho with respect to z sub 2 minus z sub 1 plus partial of rho with respect to time t2 minus t1. Okay, so kung i-divide mo niyo siya og t2 minus t1 and then transpose mo niyo rho sub 1 diri, so kanimo makuha rho sub 2 minus rho sub 1 over t2 minus t1. And then, kaning x2 minus x1 over t2 minus t1, this is just the velocity along x. So, u, kaning u rin siya equivalent. So, u, v, w. So, mo na rin yung. And then, kani, as you get the limit as t2 goes to t1, so, na yung equivalent ani. This is equivalent to the total derivative of rho with respect to t. Okay? So, mo na rin na. Kanina rin ang may mga resulting equation. And then, recall nga kaning term, or rather, kaning tulo ka term, pwede na siya ma-reduce niya nga format. Okay, so kaning tulo ka term, kung imo na siyang i-simplify, mahimo na siyang dot product of b dot delta rho. Okay? So, this term, kaning capital D rho over dt, this is what we call the substantial derivative. Okay, or the total derivative. So, this is the instantaneous time rate of change of density of the fluid element as it moves through space. So, mo ni ang change sa yang density as it moves, no, from point 1 to point 2. And then, aning d rho over partial of rho with respect to t, this is the local derivative or the time rate of change of density fixed at point 1. So, mo ni siya ang pag-change sa value sa density kung i-fix na to nga element dere, no? Kung ga-change pa ni kay flowing man na imo ang fluid. So, ga-change na siya. So, mo ni siya nga term. Rather kaning this one. And then, this one is the convective derivative or the change due to the fact that it moves to a different location in the fluid with different conditions. No, so mo ni ang mga account sa change sa density, no, sa pag-adto niya sa lain na position. Okay. So this is the first model of the fluid. Okay. So imagine that you have a fluid that is in motion. Okay. So how do you model this one? First is you model this one is a finite control volume that is fixed in space. So you consider a finite control volume. Okay? And then, instead nga evaluate nimo ang tanang properties of fluid, you'll just consider the fluid that is inside the control volume. Okay? So this is the Eulerian model. No? Ato mga fixed in space, no, evaluate nimo ang property sa fluid inside the kani nga control volume. This is the Eulerian model. Okay, so how do you derive the continuity equation? First, inside the control volume, no, ang outside ana niya, you get a small surface. Okay, so i-denote nato di siya as ds, no, kani nga surface ds. Okay, or kaya ang tibok surface area na sa imo ang volume is s na siya. So kung gamay man, since this is we're considering a small surface area, let's call this one as ds. Okay, so the change of mass inside the control volume is just the net mass flow out of control volume through surface S. Is just equal to the time rate of mass inside control volume. Okay? In other words, ang mugawas daw diri sa imo ang flow out, no? Mugawas sa imo ang control volume is just equal sa pilay nawala sa imo ang mass inside the control volume. So, mura na yung buat pasabatan. Okay, so let's call this one as B. And let's take this one as C. Okay? So, therefore, what is the formula for mass flow rate? Mass flow rate is just density times area times velocity, right? So, therefore, so unsa ang mugawas diri sa surface S nimo? Therefore, ang B nimo is just therefore, ang mass flow rate nimo would be density, okay, times density times velocity dot ds. Unsa ang mugawas diri ba? Kung unsa ang mugawas diri nga surface. Okay? This is just the dot product of the velocity and the surface area. So unsay pasabotan niya? Pasabotan na niya, no, kung naakay surface area sample kani nga surface area. Kung mo ni ang ds nimo, So unsa ang mass flow rate niya diri? Kung diri ang imong velocity, kung mo ning v nimo, mo ni ang direction, kinahanglan nimo ni kung gana sample ang gana imong velocity, kinahanglan nimo resolve. Kinahanglan nimo siya i-resolve into component na perpendicular diri sa imo ang area. No, so kani resolve po nimo kuhaon nimo ang component ani nga vector nga perpendicular dire. Ana, no? So mao na siya, mao na yung pasabot aning dot. Ang pasabot aning dot gikuha nimo kung mo ni ang area, surface area, you get the component of the vector that is perpendicular dire kay mo ra man ang molusot dire. No? Diba? So lahi-lahi man ang direction sa velocity kaya na posible ana. So kaning dot na karon ang mag-take care ana nga ang makuha sa equation is only katong perpendicular dire. So mao na siya. Mao pasabot ani. Okay? Okay, so this is kani siyang component mora ni ang mugawas sa diri nga surface area. So therefore ang B nimo karon is the summation ani tanan, no? Tibok nga air na surface. I-sum up na nimo siya. Kay surface mo na siya, so get the surface integral of rho v dot ds, no? Para makuha nimo tanang mass flow tanang surface area nimo. Okay, so unsa ning C? Now what is this C? Ang C pod is the time rate of decrease of mass inside the control volume. So first is unsa day ang mass inside the control volume? Okay, ang mass inside there is just density times volume, right? Okay, small volume ni siya, denoted by dV. Okay? Okay, so what is this kaning C? Now, in order to get this kaning C, which is the time rate of decrease of mass inside the control volume, consider a small volume inside the ring control volume. So denoted by dV. No? So unsa ang mass ani niya? Ang mass ani niya is just the density times volume. Again, if you want to get the total mass of the control volume, you sum ni mo tanang small control volume. So that is just therefore C is just the volume integral of rho dV. Volume integral. Okay? So, by the way, dili pa din ni mo C. Ano yung summation sa mga masses inside, no? Inside the control volume. Okay? Na equal man ni, no? So, niya rate man ni, niya kani mass lang. So, dapat ato ning i-differentiate with respect to time. So, therefore, sa metabuan ni, ito ning i-differentiate with respect to time. So, mauna dahil ni siya. Muna yung time rate of decrease increase. Time rate of increase. Okay? But since decrease man ang ipangayo, ang ganang paggamay sa mass sa sulod sa control volume. So, ato ni multiply of negative. Muning na siya negative. Therefore, ang C nimo would be negative partial of the volume integral of rho dV. By the way, nasa sa book no, derivation na nasa book sa Anderson. Okay, so ito na din yung equating duha. By the way, recall na to, no? Ga times tag negative because decrease man. Diba? Kung mugamay, kung mugawa sa ang mass diri sa imong control volume, siyempre mo decrease ang mass diri. So, mo na nga multiply tag negative. Therefore, what is now your equation? So, you have rho v dot ds equal to negative partial of triple integral of rho dv. Okay? So, ni-rearrange, this would become partial of rho dv plus surface integral of rho b dot ds is equal to 0. So this is now your continuity equation, no, for model of the finite control volume fixed in space. You know, finite control volume fixed in space. Okay. Now later on we will derive also the other three models. Okay, so we will derive the second model of the finite control volume, but this time this is moving with the fluid. So, sa'yo pasabot ani. Pasabot ani is that kung naa kay fluid, no? You model this fluid as a finite control volume, but this time kaganin no fix niya. So karon gauban niya sa imong flow, no? So kung mo niyang streamline sa fluid, so mag-travel ni karon imo ang control volume along this path, and then ato ni siyang i-evaluate kung unsay nahitabo sa mga properties within the control volume. Okay? Okay, so one thing to note is that during sa travel sa imo ang control volume, ang iyang mass does not change, no? The mass does not change, but ang iyang volume posible mo dako, posible mo gamay. Ano man kaya ang density po mo posible man mo change, no? So how do we derive the continuity equation? First is that let's consider a very small volume dv. Okay, very small volume, and as we have noted, ang massa ni nga small volume is just rho dv, right? Rho dv. Therefore, kung gusto nimo kuhawon ang total mass sa imong total mass aning imong volume, you just get the volume integral. Or in other words, you just sum up all this small volume. Okay? And since we are concerned with the mass flow rate, so ato ning differentiate with respect to time. Kanipod. No? So, unsay may tabuan nga term? D of mass, total mass, over dt. This is just equal to 0. Ano man? Well, there is no change of mass, no? As the control volume travels from point 1 to point 2. There's no change, so therefore 0. So, ang imong equation would be Kani di ay mahimo na lang ni siyang d over dt triple volume integral of rho dv is equal to 0. Okay, so dali ra no. So this is the continuity equation for this model. Again, kani siya pwede nimo ni ma-convert sa katong previous na to nga form, no. Okay, so the third model is that you have a model of an infinitesimally small element fixed in space. Okay, so essentially this model states that if you have fluid, you model this one as having a very small fluid element. Very small fluid element that is fixed in space. So, fixed in space na siya. Wala galihok. Again, this is the Eulerian model, no? So, how do we get the continuity equation based on this model? Okay? First of all, ang volume ani niya, ato ni enlarge, no? Kung ato ni siyang i-enlarge, muna siya, dako na siya, ana. Okay? So na, okay, you have x, y, x, y, and z. Okay, x, y, and z. So therefore, kani siya nga length is dx, kani dz, kani dy. Okay? Muna siya. So how do we get the continuity equation? First of all, ang total mass ani nga fluid element, total mass is just equal to rho times volume, which is dx, dy, and dz. Okay? Okay, so we will now model, no, ang mass flow rate nga mo pass sa different phases sa imo ang fluid element. Okay, so ato ning i-draw tag separate diri. Okay. Okay, so what is the mass flow nga mo sulod diri? Mass flow nga mo sulod diha is just mass flow rate is density times area times volume, right? And kani siya, ano man siya? Ang imong density is a function of x, y, z, and time. And also, ang imo ang velocity is a vector field or vector function. Ano? UVW. Wherein, ang kaning u nimo function po niya sa x, y, z, and time, as well as v and w. Okay? So, meaning ani, ang imo ang velocity sa imong fluid along x is denoted by u. Along y is v, along z is w. Okay? So unsa ang mas lority mo sulod diri nga surface area? Masuludanan niya is just density, velocity, u, and unsa ang area? Ang area diri is kani siya is dz. This is dz kani dy, so dy dz. Rho times u times dy dz. Tama? Okay. Okay, so mo na mo sulod diri. But what unsa pay mo gawas diri nga surface area? Ha? Unsa mo gawas dinhi? Naa pay mo gawas diri, right? Pero for now wala ta kabalo. Atong let us assume nga mo gawas diri kay F2. Okay, so what is F2? Takabalo, but we can approximate F2 using Taylor series. Okay? Taylor series. Okay, so how do we approximate? Okay, so let us recall a little bit about Taylor series na. So ang Taylor series nimo, kung naa kay function, okay, kung naa kay function, ana. Say for example, this is y is equal to, ano na lang, y is equal to g of x. Okay? And then, kay at point 1, this is a, and ang yung corresponding value is f of a. Right? Okay. What if gusto ka pangitaon nimo ang value ani kani nga point. Ang pangitaon nimo gusto niyo pangitaon is kani f of x. What if gusto niyo man pangitaon? Kung naa kay equation, dali ra kayo imo ra ni substitute diri import ni. But what if wala ka ni? Dili ka given na. So how do you approximate ang value ni? So ang ginabuhat ani sa Taylor series is you get the first derivative ani, no, kaning line. This is f prime of x. Okay? Ano? Ang slope maning f prime of x. Kung ano maling nga line, say for example p of x. P of x. So may tabuan ni karon, kung ano mang first derivative ani, instead niya f of x imong makuha, kani nga value imong makuha kani. So mo ni ang p of x. So ang difference ani nilang duha kani mo na ni ang error nimo. Okay? So kung nagkalayo ni sa a, kada kong error, so ang buhaton ani paduli mo ni sa diri para gamay-gamay mong error. Okay? So in notation, ang f of x nimo, you can approximate that one as f of a plus f prime of a x minus a. Okay? Of course, naa pa ni sa mga higher order terms, no? Pero ito lang ipotol sa first order. So, unsa may pasabutan ni? Makuha daw nimo ang kaninga value with just knowing the value ani nga point plus ang slope ani nga line kani slope ra man ni. So this is just f of a plus derivative of f of a dx times distance ani nilang duha kani nga distance x minus a. Okay? So kung ato nang i-apply dire, unsa na to pag approximate ni siya kani this is equivalent to your f of a. Ana siya. So ang f2, therefore f2 is just f of a kani rho u dy dz. Okay? Plus derivative daan eh, derivative of since duha man ni ka variable sa partial ni sa partial of rho u dy dz with respect to kani unsa ni siya giagian this is your dx respect to x times x minus a. So unsa ning x minus a again kani man na siya kani nga point o kani nga point, so dx ra gyapon na siya minus dx. Okay, so therefore this becomes kani kay constant ra man ning dy dz pwede ra pagawas, so this becomes rho u dy dz partial of rho u respect to x dx dy dz. Tama? Na lang i-bracket. No. Kana na lang. F2. So therefore kaning F2 di this is just rho u times u partial of rho u respect to x dx dy dz. Okay? Okay, so in the same way, unsa ang mosulod diri sa ilawom? Mosulod na flow kung gawas diri. So this is just rho along y v, right? Rho v dx dz. Tama? Rho v dx dz, and then magawas diri rho b plus partial of rho b dx not dx dy partial of y dx dz. Tama? Okay. Lastly, unsa mo sulod diri nga side. Ang sulod diri nga side is rho, this is the z direction, so rho w, ang kaninga area is dx dy. Rho w dx dy. And then ang magawas diri nga side is rho W plus partial of rho W to Z dZ. Then dx dy. Natin yung reason. Dx dy. Okay? Kompleto na. Okay. Since na-label na nato tanan, ito na ning isa-isa ho, no? Kung saan ang net outflow in x direction. Net outflow in x direction. Unsa daw ang net outflow ni? Ang net outflow ni is just the output minus input. So, this will be just rho u plus partial of rho u respect to x dx dy dz minus rho u dy dz. So this is just makancel ra na ini kanino kanini. Mabili na lang karon is partial of rho u partial of x dx dy dz. Tama? So in the same way, the same logic, net outflow in y direction is just equal to kanina lang ang y. Dari mo ng y. So kani partial of rho v respect to y dy dx dy dz. Okay, net outflow in z direction. What is the net outflow in z direction? Just partial of rho w respect to z dx dy dz. And then ato na din ning sum up tanan. Diri na lang ako isulat, no? Sum up natin tanan. Net mass flow out of the element is equal to time rate of decrease of mass inside the element. Okay? So net mass outflow out of element is equal to time rate of decrease of mass inside the element. So kung mao ni ang total mass nimo, no, kung mao na ang total mass, ato ning mass pa man ito pa ning i-differentiate with respect to time. So ang mahitabuan ni mo ang time rate of decrease will be change of mass is equal to partial of rho may kanay constant man dx dy dz. And then since decrease man siyempre nanggawas man no, outflow man so mo decrease ang mass inside the element, so you take the negative inig butang na to diri karon. So ato ning i-sum up ning tulo kung ning i-reason No, sama na to ni. Sum up na to tong tulo kani sa metabo ni to become partial of row u ang katong dx dy dz ato tong i-collect plus partial of row w dx dy dz is equal to the negative negative of partial of row respect to time dx dy dz till ni so this becomes sa metabo ni partial of row ito ni transpose because plus partial of row u plus partial of row v plus partial of row w respect to z equal to 0. Right? Or, simplify pa na ito ni partial of row plus del dot row v. Okay? So, kung i-evaluate nimo ni evaluate nimo ni sa pag-evaluate kaning delta this is just partial of I partial of yj plus partial of z k. Right? Ang v nimo ang row v nimo kaya ang v nimo is kung man so may mo ning row may mo ning row ui plus row v j plus row wk. So kung i-dot nimo ni karon kani siya dot kani ang mo result. So this is the third continuity equation. Okay, so this is the last model for our continuity equation. And now, we have a model of an infinitesimally small fluid element that is moving with the flow. So, this model states that you can model a fluid in motion by having a small fluid element and then kaning element mag-travel na siya along the flow and then we evaluate the properties now as it travels along the streamline or path line niya. Okay? So how do we get the continuity equation? So this small fluid element has small volume dV. Therefore, ang mass niya is just rho dV. Okay? Again, ang say implication ani nga model. This model states that as it travels along the path, there's no change in mass. Okay, so kung ato ni siyang i-differentiate with respect to time sa metabolic kani just equal to 0. Okay? Therefore, sa metabo dt of rho dv is equal to 0. Diba? So kung ato nang evaluate, this becomes second the first the second. Okay? And then multiply this one by 1 over, so this becomes 0 over dt plus rho times 1 over delta b derivative of over dt is equal to 0. Okay? Okay. Now, kaning term is just equal to, may mura kaning equation, may mura rin siyang d rho over dt. Just look at the book by Anderson na niya dito ang i-describe yun sa pag-derive ning from gikan ani equivalent ra daw ni siya sa rho delta dot b. Okay, so may muna din yung rho delta dot b is equal to 0. So, dili na ako na ipakita direct kay na dito sa book. Okay? Okay, so this is the equation for this model. Okay? Okay, so in summary, these are the different forms of the continuity equation. Okay, we have first is the finite control volume fixed in space. And this one is the for finite control volume that is moving with the flow. This one for an infinitesimally small element fixed in space, and for the infinitesimally small fluid element moving with the flow. Okay. Now we will have an example wherein we convert this form into another form, and you can do that by following this diagram. Okay. So, i-observe niyo ning arrow. This form can be converted into this form. This one, kani, convert mo paana. Okay? So, sample, we will convert form 1 into form 3. So, nana there is a book by page 57. Okay, so this is form 1, and we will convert it into this format. So, in order to show that these equations are just one. Okay? So, since this equation is taken from a finite control volume that is fixed in space, so the integration is constant. No? Okay, fixed man siya sa fixed man tong imong control volume. So, kaning derivative pwede sa is rho dere. So, this becomes naning form. And then, applying the divergence theorem. So, ang divergence theorem, ang equivalent ani niya, pwede nimo na siya, diba? So, this is a surface integral. This is just equivalent to ani. Okay? Just tanawon lang ninyo unsa ning divergence theorem na may equivalent na format dito from our previous lecture, no? So, mao na siya ang equivalent niya. And then, pag change nimo ana, so what becomes is that pareho na sila nga volume integral, and then with the same kani dv. Okay, so pwede naman na siya i-combine. So that is why partial of rho with respect to time plus delta dot rho v dv is just equal to 0. And then, since the finite control volume is arbitrarily drawn in space, meaning para ma-evaluate daw ni siya nga, para mahimo ning 0, dapat kani nga term diri within the integral, dapat ang equivalent ani niya is 0. So mao ni siya. Partial of rho with respect to t plus delta dot rho v is equal to 0. So this is the kani third model. Okay? And the rest, nara sa book, yung i-convert, no? So, just review this one. Also, try to derive it yourself para ma-familiarize ninyo. Okay? Thank you.